So last day we defined the stochastic integral for the closure of the span of all simple functions under the norm L2 of lambda t product with p. Um, and then we saw that the properties of this the properties that the simple integrands satisfy, they are also satisfied by the closure of their span. So here was a mistake that I made yesterday, last day, that I said that this ET closure, we are taking the closure under the norm of MT2. So MT2, recall, is the norm given by this one, this expectation of supremum up to time t, the square of the supremum up to time t of ms, and then we raise it to the power half. But this was a mistake in my part because this is not defined for ET. This was defined for continuous martingales. Yes. So this should be correct. So L2 of lambda t product with P. We should take the closure under this norm. And we saw the Ito isometry holding true, and we saw that this the quadratic variation is also given by the integral of 0 to 2 ft whole square dt, like in the simple integrand case. And lastly, we stated this theorem which tells us how to evaluate a stochastic integral for f in this space L2 of lambda t product with p, um, which satisfy this notion of mean square continuity as I defined it. So mean square continuity means that limit s tending to t of the expectation of fs, comma fs minus ft, this whole squared should go to 0. So if that holds, then we have this useful way of evaluating this integral. So this essentially becomes a Riemann-like sum. So that and we then take the limit L2 limit, and this norm as this norm pi goes to 0. So norm pi is the partition with points sj up to from 0, sj equals to 0 to n. So today we'll start with the proof of this above theorem. So the proof, so for each partition pi, we define f pi of t comma omega to be the sum f s j minus 1 omega is the indicator of sj minus 1 sj of t. So this is a simple function, as you can see, um, and as f belongs to this L2 of that norm, we have that this this simple function f pi of t omega, this will also lie in the L2 because these are just so we are taking one up to certain intervals, so that is shorter than the whole interval of 0 to t, 0 to capital T. Um, so pi, oh sorry, I did not complete this line. We have f pi of t omega belongs to this L2 of lambda t cross p. So we can define the stochastic integral of f pi. So by Ito's isometry, we have that expectation of the integral f 0 to t f of t minus is f pi of t uh, dbt whole squared. This is equal to 0 to t of expectation of mod of f of t minus f pi of t uh, whole squared and then dt. So now the we can write these integrals from 0 to t. We can break up this integral as this sum 1 to n of integral sj minus 1 up to sj. It is we are just looking stepwise. We have just looking at this stepwise. So because the f pi's are defined stepwise, so this becomes f of t minus f of sj minus 1 whole squared and then d. And this is less than equal to when sj minus 1 up to sj of the supremum of uv belonging to this small partition sj supremum of this expectation of f of u minus f of v whole square dt. So I hope this step is clear. I mean, we were just subtracting f of t minus f of sj. So this is lesser than equal to the suprema over uv belonging to all of these belonging to this interval of f of u minus f of v, and then we are taking it. Then everything else remains the same. And the point is that since we have that mean square continuity notion, we should expect that this should go to zero. This quantity should go to zero as this norm of this partition goes to zero. So we have that this goes to zero as the norm of this partition goes to zero by the uh, by our assumption, this one. So so we have that j equals to 1 to n of sj minus 1 of times bsj minus 1. So notice that um, if we want to compute the stochastic integral of for f pi, then we would get this particular thing. So is the cursor visible? Uh, is the
Yes,
cursor?
yes.
Okay. So notice that if we wanted to compute the stochastic integral of f pi, then we would have gotten this expression. But we want to do it for f, and we want to take the L2 limit. So that's why this expression, this is equal to 0 to t of f pi of t dbt, and what we have shown is that as norm pi goes to 0, in the norm lambda t cross p, we have that f pi, um, sorry, not in the norm not in this norm, but in the usual L2 of p, this set of random variables, that is integral of 0 to t of f pi of t dbt, that converges in L2. So that is a random variable that converges in L2 of t to integral of 0 to t f of t dbt. So this is what we have shown. So this converges as norm pi tends to 0 in L2 of p to integral of 0 to t f of t dv. So this gives you a way to compute this integral using a Riemann sum sort of argument. So, uh, so maybe I'll just show an application of this. So what if we have f of t comma omega equals to bt? That means we want to evaluate integral of 0 to t bt dbt. Then what would this give us? So first, first notice that bt squared, this is equal to summation of j equals to 1 to n of bsj minus bsj minus 1 and then whole squared. But this is just writing in terms of the partition. So there's nothing in this. Um, and this, if we expand this square now, we will get summation of j equals to 1 to n of bsj minus bsj minus 1 uh, whole squared plus 2 times summation of j equals to 1 to n summation of k equals to 1 to j minus 1 of bsj minus bsj minus 1 into bsk minus bsk minus 1. This is just the usual a plus b whole squared formula. And so I think in 2 to 3 lectures before, Sudesh Nadi proved that the quadratic variation, not the quadratic variation, sorry, that is the uh, two variation. I think it was called the squared variation that converged in L2 for Brownian motion, that converged in L2 to T as the norm of partition goes to 0. So, so that's why this term is nothing but this uh, the quadratic variation. This should converge to T as norm pi goes to 0. And so here for this term, we can first sum the k equals to 1 to j minus 1 many terms, and we can write this as equal to 2 times j equals to 1 to n of bsj minus bsj minus 1 times bsj minus 1. So notice that this, if it's the sum from k equals to 1 to j minus 1 of this sum, these terms, we should get bsj minus 1 as our answer. And this we have already shown by this formula. This we have already shown that this converges in L2 t as this norm pi goes to 0 to 2 times integral of 0 to t dt dbt. Um, so what have we shown? We have shown that bt squared equals to t plus 2 times 0 to t dt dbt. So in other words, we can rewrite this as bt squared by 2 minus t by 2 equals to 0 to t bt dbt. So I want to make some comments about this. So this is the fundamental difference between our usual calculus and stochastic calculus. So for example, if we wanted to integrate x dx, or let's say for any differentiable function, we want to integrate f of x df of x. So by our usual calculus rule, we just write it as f of x squared by 2, right? I mean, assuming f of 0 is 0. So we just write f of x squared by 2. So that is our usual calculus rule. But here in stochastic calculus, you don't merely have this term bt squared by 2. So you are integrating bt dbt. We don't directly have this term, but we have this minus of t by 2. So this is the factor which is causing uh, all the new that is the source of all the new things that is associated with stochastic calculus instead of the normal usual calculus. And so like I said, so this is this thing, this bt squared equals to t plus 0 to t bt dbt. This could have been proven using Ito's formula. So this is just we are applying Ito's formula to the function x squared to bt. So uh, it's okay if no, it's okay if one hasn't seen Ito's formula yet. So we are going to do that. So but the thing is that um, we are going to use this particular theorem in some sense to prove Ito's formula, or at least we want to use the idea given by this theorem to prove Ito's formula for this L2 of lambda t cross p valued uh, uh, processes which have that norm finite. L2 of lambda t cross p, that norm is finite. So I hope this example was clear. Um, so now I want to make some other. I want to state a result, but I don't want to go into the proof of this. So if you remember, we started. Sorry. What happened? Okay. Um, so if you guys remember, we Ganeshwar was saying something about progressive measurability a few classes back. So where does progressive measurability come in? Hello, am I audible still?
Yes.
Okay. So there's some disconnection happening with the tablet. So yeah. So uh, Ganeshwar was saying something about the progressive measurability 2 or 3 classes back. So where does that come into play in this scenario? So from last class onward, I have not even used that term, but that term is actually closely related. So in the sense that what so if you remember, we took the closure um, here we took the closure of this span of simple functions under the norm L2 of lambda t cross p. So as it turns out, uh, this closure is actually this closure et bar uh, closure under the norm of L2 of lambda t cross p is this script p, where p is the set of all progressively measurable L2 of lambda t cross p functions. So since we were taking the closure of all simple step functions, one could have expected that we will get the whole L2 space. So we do not. So that's the point here. So we get the closure is the set of all progressively measurable functions. So this is almost all of L2 of lambda t cross p functions, for but we are excluding things which are not progressively measurable. So last day, I and Korombir were talking about what can be examples of non-progressively measurable functions. So one canonical one is that we just embed a Vitali set um, in the interval 0 to t, and that makes the Lebesgue thing non-measurable. So that is a trivial sort of example, but can we have any real world example which has got to do with real world phenomena? So for example, in case of uh, s- stock manipulations or some if people remember, there was some a bitcoin prices rose up by a lot. So I'm saying that example because this stochastic integral of f of t dbt, this is nothing but the profit that one makes in time t by betting on a Brownian motion, where f is our bet. So for some reason, if for some reason the person who is betting comes to know of things which are not yet determined. So for example, in match fixing and all those things. So if so in that case, this f would fail to be this progressively measurable, because in time t you are knowing more things uh, than the interval 0 to t and the Brownian motion up to that time 0 to t is telling you. You are knowing more things, and or you are knowing things which are not measurable under that norm. So hey, this was a bit of a digression. I hope that this thing is clear, that it is the closure, but I don't want to go into the proof of this because uh, it will take some while, and it has not. I mean, we don't really gain anything except for major theoretic results. Uh, so another thing I don't want to go into the whole proof of, but I think it's important to state, is that there is a concept called localization in time. So what is this? So again, in our setting, f belongs to L2 of lambda t cross p, and it is progressively measurable. So uh, and just we can write this intersection p for now. Um, and so the result, so what this means is that uh, we have integral of 0 to t of f of t dbt, and this was it's better to write f of x. So remember that this is a martingale. This is a martingale. So we can, so for a stopping time, okay, let me just write that first, and let tau be a stopping time which is adapted with respect to script ft and all that. So the thing is that if we look at this martingale f of s dbs and we stop this process, so what can we expect this process to be? So stopped process of the stochastic integral. So the theorem or that actually this was part of that big lemma that we proved last time. So we have that the stopped process uh, 0 to p of s dbs in tau. This is the same as the integral of 0 to t of f of s. Now in the integrand, instead of b, we want to take uh, this stopped Brownian motion, and this is also equal to integral of 0 to t of f of s indicator of 0 to tau dbs. So this might look a bit confusing at first. So what's happening is that we can, this itself is a martingale and we are looking at the stopped martingale, and we are saying that this is equal to the integral of fs with respect to the stopped Brownian motion, d of the stopped Brownian motion. So we know so we had defined for general martingales, for general continuous martingales, a stochastic integral of general continuous martingale. So bs mean tau. This is a stopped martingale, and this is also equal to, we just bring tau into this, we can bring tau out of this dbs mean tau, but we can just write it with we can just associate it with f. So we can take the integrand to be f of s indicator of 0 to tau, and then we can perform the integration. So these all give the same thing. So the reason I don't want to go into the proof of this is because this is proved in the same way like we do Doobb's maximal inequality for the continuous processes. We first do it for discrete times and then we approximate for the stopping time taking our real values. We just approximate the stopping time from above by discrete stopping times. So that takes a bit of work, but maybe I can just um, maybe I can just write it, do it for the discrete one. So suppose, so suppose tau takes values s0, s1 up to sn. So tau just takes finitely many values, and these values are just s0 up to sn. We can assume that tau takes these values s0 up to sn. We call it s0 up to sn where our steps in this simple function. So sorry, I want to prove it for simple functions first. So not for L2 functions. So uh, for simple functions, this s0, s1, those were the steps that we took. But since tau is taking finitely many values, we can assume them to be those step points, because in case they are different, we can just add more to the partition. That makes no difference in the expression of f. We- we're just adding more points to the partition, so we can do that. And so we have f. So now consider a martingale, not necessarily Brownian motion, and this is just continuous martingale. So we can write f fs dms, and we can look at this stop process t of t mean t, and this is equal to j equals to 1 to n sj minus 1 m sj mean tau mean t minus msj minus 1 mean tau mean t. So this is just by usual martingale property. This, I mean, if we are defining a martingale by taking the martingale transform of a predictable process, so this is the expression we get for stop martingales, right? So this is just the usual martingale thing, and this is equal to uh, j equals to 1 to n of sj minus 1. So since we took tau to be taking values in this set, we can just write it as m sj mean t. Sorry, what do I want to say here? Uh, sorry. This is ah. So again, so by definition of the stochastic integral for step functions with respect to this martingale now, so m of t mean tau with respect to this martingale, this will be equal to integral of 0 to t of f of t d m this should be s mean tau. So this is our statement here, and we can write f of indicator 0 to tau, uh, integral of this dmx equals to summation of j equals to 1 to n of f of sj minus 1, indicator of tau greater than sj minus 1, indicator this, and then we have m m of sj min t minus m of sj minus 1 in t. So we can write it like this, and this equals of sj minus 1 sj min t minus c minus 1 min tau min t, and this is again by definition, this is 0 to t of f of t dm of min tau. So this gives you the equivalence of these three. Um, so this was for stopping time taking finite values. So for stopping time taking discrete values, we can approximate that by stopping time taking finite values, and for stopping times taking continuous values, we can approximate them by discrete values. And also we want to approximate f. So we took f to be simple functions. We can approximate f for to be in this L2 of this space. Then also this theorem will hold. So this is what is called the localization in time. So this is one thing that I wanted to state, but I don't want to prove. Um, okay, so the next thing that should be on our agenda is Ito's formula. So some motivation regarding this. So recall the integration by parts formula. So we write f of g of t minus f of g of 0 equals to integral of 0 to t of f dash of uh, this is not integration by parts actually, this is just usual integration. Sorry, this, right? So
Change
yeah,
of variables.
hello.
Yeah, this is just change of variables, right?
Change of variables. Yeah, yeah, yeah. I got confused. I termed it to integration by parts. Yeah. So this is just change of variables formula. So this is valid for g belonging to C1 functions. But what can we say about f of bt minus f of b0? Well, b0 is just 0. But what can we say about this? So intuitively, this should be this f dash of bs times bs dash ds. But unfortunately, this does not make any sense. So we have to go by another way. So here, Ito in 1942 proved this remarkable formula that allows you to do change of variables, and it is this f of p0 equals to 0 to t f dash of bs dbs plus half of 0 to t f double dash of bs t. So you want to define f for f belonging to C2. Um, so this is a basic version of the Ito's formula for just Brownian motions. So there is a general one for more general Ito processes, which are called Ito processes, and there's a notion of stochastic differentials. So I'll I'll I, I'll do those, but for now let us just focus on the Brownian case because those are also very important. We have to do those. So, but for this particular moment, let us focus on the Brownian case. So where does this formula comes from? So if you look, so this term is okay up to this first term, this f dash of bs dbs. This term is the same as this term. So up to this term, this is what we expect. But this is the additional term, and also notice that this integrand becomes ds instead of dbs. So some heuristics here. So if you
So, Argyadip,
huh,
so earlier when you did this integral of ds dbs, so
dt,
that's just a special case of this thing, right?
yeah. So I can just write this. So we took f to be x squared, or did we? Or did we just took x? Did we just take x? I think.
No, I
We
think
took
it
x
was
squared. X squared.
x
Yeah.
square. Yeah.
Yeah. So we should get bt squared minus b0 squared equals to integral of 0 to t. So f dash would be 2 times bs dbs plus 1 by 2 times, so f double dash is 0 to t, f double dash is just what is that, I 1, so this is just ts. So this gives you that bt squared equals to 2 times integral of 0 to, or I just write it, this is, so this is just t, right? This is just t. So bt squared minus t equals to 2 times the integral of bs dbs. So it's really that simple. So so that formula is a Riemann sum. So Riemann, even if they are Riemann sums, it's not very easy to evaluate. But Ito's formula gives you a, in a hands-on way to just directly compute these things. So uh, the heuristics is as follows. So how does this formula come? So what is the intuitive reason for that?
So, uh, is that t
Yeah.
by two?
Uh, f double dash, so there will be a 2 here, sorry. So
Uh-huh.
f double dash is 2, f double dash of x is
So,
2,
so
so
if I
half into 2, so 2
right,
and 2
so
cancels.
if I know how to integrate bs dbs, uh, then I should be able to cover most of the functions, right? Or
Yeah, actually that. So this is one of, this is, you can take that, take this to be a one of the most useful identities, you can say, about stochastic integrals, right? So you can say many things from this. So for example, this
right. So,
bs dbs, huh?
yeah, take that as a, probably I could take that as a black box and just proceed to compute many integrals.
Yeah, compute. So for example, whenever this bs is showing up, so for example, if you want to go for b to the 4, so what, so what would happen? So um you take f to be x to the power 4, right? And here you would get bt cubed dbs, and then sort of one can even iterate things like that. And so there are many manipulations that that can be done.
Yeah. So basically, if I could, as long as f is integrable, then I think it's a easy thing, right?
Yeah, so f is c2, f is always integrable, and if f is very nice, then we often have very nice formulas like this. So here, so this tells you that integral of 0 to the bs dbs, so this is equal to bt squared minus t. So so this left hand side, this has nothing to do with integrals anymore. This is just one particular random variable. So, and this is like you can compute the expectation, compute the variance, so everything can be done, right? So expectation is always 0 because this is a martingale, but variance and those things can be also done. It essentially tells you the distribution of 0 to t bs dbs in terms of this. Um, so, um, so as I was saying, so this, recall that del bt is just, by del bt I mean this thing, d of t plus del t minus dt. So recall that by Brownian scaling, this can be written like this, times root of del t, right? And this is just standard Gaussian variate. So this equals in distribution to a root of del t times n, a standard Gaussian n01. So um, the mod of del bt, this behaves like a mod of root del root del t times the norm of a mod of a Gaussian. So how does this behave in expectation? So how does, so what is the expectation of the mod of a normal? So we can say that we can expect the behavior of this to be times 2 by pi. So I think this is the variance, this is the expectations. So if I'm not wrong, so this is just del t times 2 by pi. So in other words, this dbt is expectedly behaving like this. Equality is not really an equality. I'm just saying heuristic stuff. So this has expected behavior like root 2 by pi dt, and we have from here, from above, we have del bt squared is like del t, and you have a normal variable squared. So this expectedly behaves like del t times 1 because the variance of a normal variable is 1. So this dbt squared behaves like dt. So this is a uh, fundamental idea that one should keep in mind. So I remember when Manjunath taught us this course. So he told that in the last stages of the course, when he was proving Donsker's theorem, he told that if you did not learn anything from this course, I mean, what is the single most important thing that we learned from the Brownian motion course is that in time t, this Brownian motion moves a distance root t, and that is also the same heuristics that works for random walks. So in time n, we move a distance root n. That is why this scaling Sn by square root n works actually. So this is what will help us further understand the Ito's formula. So if I now ask you to expand fx in the Taylor series, so we can write it as f of 0 plus x times f dash of 0. Um, sorry, 1 second.
Yeah,
Why is
Arjun,
it
before
stuck?
that,
Huh.
I have a small question. So, so I I understand that it's a non-rigorous but formal thing, right? Like dbt square
Yeah,
equals.
yes,
So,
yes,
even like that, just by formal manipulation, what would be a immediate public use of that? Like, could you show something?
yeah.
So,
So that is why I'm stating the Taylor's
okay,
theorem. So because so in Taylor's you get this x squared. So this, right. I mean the next term would be x squared f double dash of x, right? And instead
yes,
of
yes,
x, we should place d. We should use bt, right? So that's where the thing will come in. So I'll just 1 second. This thing is disconnecting for some reason. So yes, so or so this plus we have x squared f double dash of 0 by 2. This is just plus other terms. So this is just Taylor's theorem. So if we want to express the differential df, we write it as df dx times we have dx plus um, we have f double dash of 0 by 2 factorial. F sorry, this is f d2f dx2 1 by 2, and we have dx squared plus dot dot dot. So in usual calculus, what happens is that when you divide by dx, only this first term survives, and this term, these are all of the small o of dx. But if we use Brownian motion instead of x, so if we replace this dx by dbt, for example, so then we would have uh, df equals to df dx dbt plus 1 by 2 d2f dx. By the way, these are all evaluated at bt. So, so this is just writing Taylor's formula. They are evaluated at bt, and we have dbt squared plus dot dot dot. So here, if we want to find now df dt, so the thing is that this term is of order root t, and this term is of the order of dt. So this is by this thing. So this gives you dx dbt. So these terms, when divided by dt, so if we divide this whole expression by dt, so these terms will still survive. So these terms don't vanish. These terms are not of the order of small o of dt.
after dividing by
So
dt, why does the first term survive?
So I mean by survive, I mean they don't go to zero, right? Because this is of the
db
order of root t.
root t, yeah, but you divide by t.
Yeah, and we are taking limit as t tending to zero. So it's 1 by root t, sort of.
Okay,
So that does not go to zero, right?
right, but it does not go to constant as well. But
No, no, no. This is all informal, anyways. So
okay, okay,
what I'm saying is that in case of real calculus,
right, right,
in
yeah,
case of, so here if we divide by dx, so all terms from these should vanish. So these terms should not play any part in integration, right? In case of the change of variables.
okay,
But here these two terms are the problem causing terms. After this we have root t to the power 3 by 2 and or root dt to the power 3 by 2 and all those things, they will go to zero.
okay, okay.
So if you now check, from the Ito's formula, so we sort of have exactly this. So df, so from this we can write f of bt minus f of b0 equals to the integral of 0 to t of df dx evaluated at bt. So that's f dash of bs dbs. So we want to integrate, and plus we have 1 by 2 integral of 0 to t f double dash of bs, and now we just have ds. So this is a sort of informal derivation of Ito's formula. So I know that I could have explained it better. Um, so okay, wait.
No, no, I mean this was like good enough for me at least. So
Yeah, I mean
yeah.
I could have been more clear. So uh,
No, so dbt square is like dt, right?
dbt squared is like dt, yes.
Okay.
And so uh, what's happening is that we are expanding this out in full, and we are saying we are just replacing dx by dbt, and we are directly replacing dbt squared by dt. So that's what we are getting. And then we are just applying integration. So integral of df evaluated at bt should give you f of bt minus f of b0, and then I mean, then here also we should have integral, here also we should have integral, and
Right,
the
right,
rest of the terms should go to zero. Rest of the terms should not play any part, because if we are integrating, so integration would reduce this factor dt by at most 1, right?
right,
So,
right.
yeah, and so once we have powers of the form 3 by 2, even if we reduce by 1, we still have root t times, sort of a root t behavior, which should go to zero.
Yeah, yeah, yeah.
So this is the sort of heuristic derivation, but obviously this can be fully rigorously proven using the
The
techniques we
whole,
saw.
yeah, yeah. I mean the whole
Yes,
thing, the Ito's formula and everything that you did was making it this heuristic rigorous, right?
yeah, yeah.
Right,
So the main, now our main task would be to make this entire heuristic into something rigorous. So this formula can be proven. It will take a bit of time, but it can be proven using the techniques which we saw earlier, like we approximate by Riemann terms and all those things,
right.
and we can then then after we have done it for BT, we can do it for general Ito processes. So Ito processes are basically a Brownian motion plus some drift which changes with time. So those processes we can define Ito's formula, and so there there will come the notion of stochastic differentials. So that is very important. Uh, so the main, I think, as far as I have learned till now, the main idea is the main what to say, the main um, motivation or the main target is to get used to uh, differentials, stochastic differentials. I mean, the manipulation of differentials that we do for calculus so easily, the main target is to get used to those manipulations, but for stochastic calculus. I mean, uh, uh, that so far I have understood that should be our main goal. And then, so if I just say a few, just one more minute, if I just take, so after Ito's formula, our main target should be to prove some, to see some applications, like we can look at Dolian dead exponentials, which are the exponential martingales. Maybe you can see Novikov's theorem and all that. And then maybe you can go to Girsanov's theorem. So Girsanov theorem is another very, very important application. So the Cameron Martin Girsanov theory.
Yeah.
Yeah. And then maybe we can also see Levy's characterization or of Brownian motion. And
Yeah.
yeah.
Or I was hoping maybe we could look at any small papers which do actually use stochastic calculus.
Yeah. So I am reading one now by Wang, Min Wang. So
Okay.
there is a nice application of
Okay.
Girsanov's
So
theorem.
I came across. I mean, I heard about one paper of Soumik Pal, which was some 3 page proof of certain theorem using stochastic calculus. So, I mean, I haven't even looked at the paper, but I was told that some probability, some martingale or some something related to geometry, convex geometry, certain theorem
Yeah.
was given an
Yeah.
alternative proof using stochastic calculus. So yeah.
Yeah.
So this is
Many. So, for example, Levy's characterization that can also be proven directly, but it takes a lot of work.
right.
But stochastic calculus reduces that. So, for if you guys know about local times of Brownian motion, so heuristically, it is the amount of time the Brownian motion spends in a particular level. So, for example, if you take the level A greater than 0, it is the amount of time. So, this amount of time is a loose, I'm saying
Yeah.
loosely.
Right.
Yeah.
Right.
So,
Right. Right.
so the existence of local times and Tanaka's formula, so that can be easily proven using Ito's formula. So maybe we can also see that.
Right.
It's a very nice proof. It's a small argument by
Right.
approximations. Maybe we can see that as well.
Yeah. Sure. Thanks a lot, Aryadeep. I think we
Yeah.
can end it.
Thank you.
Thank you so much. Uh, yeah. I mean, probably we can need not have next week because Monday and Tuesday we still. I mean, we'll be having this postdoc symposium. So,
I see.
I think
I see. Yeah.
we should be fine if we don't have it next week. Probably we can meet the week after.
Okay.
Okay.
I mean, I'm
Right.
fine. I don't. I am not speaking there. So Korombir, I think, is speaking.
Yeah.
Um,
No, I think it would be better if
yeah. Next
uh,
week. Next week
yeah,
is off. Then it's
yeah.
best for everyone.
Right.
Yeah.
What do you
Okay.
think, Sudeshna? Is it you think it's
Yeah, we can skip it. It's fine.
okay? Great.
Yeah.
Thank you.
Okay.
Let's meet next week, the week after.
Okay.
Bye.
Thank
Good
you.
night.
Thank you.
Yeah.
Good. Yes.